So our next paper is titled Combinatorial-Randomness-Based Power Amplifier Dataset with a RF Fingerprint Classification, and will be presented by Jiachen. He's a PhD student at Carnegie Mellon University.
Hi everyone, my name is Jiachen Xu. I'm a PhD student at Carnegie Mellon University. I'm from the Energy Efficient Circuits and Systems Lab. So today's my presentation topic is the combinatorial randomness-based power amplifier datasets with RF fingerprint classification. Due to the manufacturing variations, the different devices will show different radio transmission characteristics. So we can say that each device carries their unique fingerprint. And the same signal transmitted from the other copies of the devices will show their variations. Therefore, we can utilize this feature to have a physical layer authentication scheme on top of the traditional encryption solutions using the RF fingerprint. And also the machine learning methods have been popularly utilized to classify the RF fingerprints. Recent works show that the RF fingerprints can actually be imitated. Therefore, in this work, we propose to use a reconfigurable power amplifier to alter the device RF fingerprints over time, so we can achieve a single device multi-RF fingerprint scheme for the secure communication. So power amplifier is one of the most major factors that contribute to the RF fingerprints. We slice. To make our power amplifier combinatorial randomness-based, we slice the PA transistors into 12 subsets, and enabling 9 out of 12 the subsets will provide a combination of 220 configurations. And we can actually alter the subsets over the time to achieve the time-stamped RF fingerprint to prevent the imposters from imitating the device RF fingerprint. So the data set we are releasing here are the BLE packets collected with the analog devices mixed signal front end, which has a direct RF architecture. We use that transmitter and receiver, and the BLE packets are transmitted through our power amplifier, and the 1 megabits per second BLE packets are stored in the 25 megasample per second on the device, and the preamble and the access address are extracted for the RFF classification. Also, we collected the dataset at different signal-to-noise ratios. And there are some methods to visualize the RF fingerprint. So, for example, there's a discrete Gilbert transform-based method, which is similar to the Mellon spectrum in the audio, and we can plot the distributions of the features in the frequency domain to see the RF fingerprints. And there is a 2D plot of the t-SNE result across the collected packets from the power amplifier configurations. And in this work, we use an example convolutional neural network to demonstrate how the RF fingerprints are classified. And here we are using a lightweight model. It only has 2 conv layers and 2 dense layers. The input format to the CNN has 2 channels, which are the in-phase and quadrature samples from the BLE packets. We use a preamble and access address because there are these information are always fixed. Also, to estimate the receiver's size system-level hardware cost to deploy the system on the edge devices, IoT devices, we simulate the different ADC sampling rates and bit resolutions by decimating the raw data and quantize the data. So we found that with the symbols per sample equal to 5 and bit resolution equal to 10, it already gives a very good classification result of over 98% of accuracy to classify the 220 configurations. Also, it is expected that some configurations in the power amplifier would exhibit similar RF fingerprints. Therefore, we can actually drop some of the configurations to improve the overall system classification accuracy. Also, like it's more desired if the training sample would be low to make the development and deployment of the system more feasible. So we found that the CNN will lose its ability to classify the RF fingerprints when the communication environment is worse. For example, if the SNR transits from high to low, and so currently the way we classify the noisy training dataset is we also include some datasets that are collected within the noise environment to improve the system overall accuracy. But it would be more desirable if a model trained within one environment would be able to classify the signals from the other environment. So the conclusion here is that we have the Combinatorial-Randomness-Based power amplifier, and we collected the dataset, we released the dataset, and we use a lightweight CNN for the RFF authentication on the edge devices. Also, what remains a challenge is that the machine learning model needs to be robust to the change of the wireless communication environment. So probably we need some data augmentation methods to address that. So that's all, and feel free to ask me any questions.
Yeah, I'm Swapnil from UCLA. So your goal was to differentiate, I guess, between RF devices, kind of like, authentication, I guess, So how many devices does your dataset have? How many different devices?
So here we are trying to, traditionally each device carries their unique own fingerprint. Mm-hmm. But with this power amplifier, each device, for example, in this case, we can have 220 unique RF fingerprints that can be distinguished from other devices.
So, I suppose you trained your model to distinguish between 220 different devices. So what happens if I bring in, like if adversary brings in, an LN device? Like, is your model going to detect it as an LN device, or is it going to probably classify it as something within, those 220?
Yeah, that would be similar, something like the anomaly detection. Yeah. Mm-hmm. So this model here is only like classifying the configurations within this device. But in order to achieve, like if there's a new device coming in, I don't want to classify like there's a new device, we need another maybe a classifier that is doing the anomaly detection job.
And
yeah, but
do you think it can scale beyond like 220 devices? Do you think, so what you're doing is using something known as physical unclonable function, I guess, assuming that, your RF hardware has, some form of entropy, which allows it to be distinguishable, from each other. So do you think it's scalable? Like, can it scale to like, thousands of different devices? What do you think?
Yeah, the scalability really depends on the machine learning model that we are building mm-hmm. there.
Mm-hmm. Okay, thank you.
Tony from Resilience. It was a great question about the scalability. I'm not sure how, but instead of a classifier model, you could use something like a Siamese network and be able to, instead of doing classification, you would just be doing something where you're identifying like a latent space of what all of these things are. And then that way it would be a lookup kind of table of what's what, and if it's not in the lookup table, it's a new device. And if your latent space is right, you should be able to get something that says, well, it's not anything I know, but it's in between the following types of hardware. So I know it's something in between. It's like these things. So instead of a classification, you could just do like an autoencoder with a latent space.
That's a great point. Actually, instead of your model confidently telling that a LN device is within the classification, your model should output like some confidence interval or something that, okay, I'm not probably sure if this device exists or not, I guess. Yeah, that's what he was suggesting.
Yeah. So basically there should be one more class, that's what he's saying.
Yeah, that's so like for this kind of question, so it's very similar to the anomaly detection. So like, so we want to make this system scalable. Like when new devices are coming in, we want to also classify those new devices. Yeah, we can include another device, another class in the classifier. Like it's an outlier or or something.
This is actually great conversation. You can take it offline.
Yes. I think, yeah, so that's all for this paper, I guess.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.